What are the challenges of biological signal amplification? Imagine trying to hear a whisper in a noisy room. That's similar to what amplifying biological signals involves. These signals are tiny and easily drowned out by background noise. One big challenge is their very low amplitude, often just microvolts or millivolts, which makes them highly vulnerable to interference. To get a clear reading, amplifiers need to have extremely low noise levels, but achieving this is tricky because all electronic components generate some noise. Another issue is the need for very high input impedance. This means the amplifier must draw minimal current from the biological source so it doesn't alter or load the signal. Designing such high impedance circuits is complex, especially when trying to keep the device small and portable. Speaking of size, many biological signal systems are meant to be wearable or implantable. That means the amplifiers must be compact and consume very little power to avoid draining batteries quickly or generating excess heat. Biological signals are also very diverse. They can vary widely in strength and frequency. The amplifiers must stay linear across this broad range to prevent distortion, which can hide or change important information. Nonlinearities can introduce unwanted artifacts, making it harder to interpret the signals accurately. External electromagnetic interference from sources like power lines or wireless devices can also disrupt the signals. Proper shielding and filtering are needed to block these interferences without losing the biological signals. For implantable devices, biocompatibility becomes a concern. The materials used must resist corrosion, avoid causing tissue reactions, and stay stable over time. Otherwise, the device might fail or produce unreliable readings. Biological signals are often complex, with overlapping frequencies and nonlinear responses, so amplifiers need advanced designs to handle this complexity without losing key details. Environmental factors like temperature changes and chemical variations in the body can also affect performance, so the amplifiers must work reliably despite these fluctuations. In real-world applications like neural recording systems or electrocardiogram monitors, these challenges are addressed by designing circuits with high input impedance, low noise, and low power consumption. For example, neural amplifiers are built to pick up tiny neural potentials accurately, while wearable heart monitors use specialized operational transconductance amplifiers to keep signals clear and power use low. Overall, successfully amplifying biological signals involves balancing electrical performance, environmental stability, and miniaturization to ensure accurate and reliable data collection.